Now moving on to another very interesting result about threshold functions. Okay. So definition. A function f from 0 1 to the power n to 0 1 is said to be symmetric if for all permutations sigma, okay, belonging to Sn, f of x1 to xn equal to 1 if and only if f of x sigma 1 x up to x sigma n equal to 1. So essentially what this is saying is that a function is symmetric if no matter how you rearrange the input bits, it will have the same value. That's all. Okay. So irrespective of the rearrangement. So Sn is the permutation, I mean it's the basically the set of all permutations of size n. Okay. So what we will show is threshold or not threshold. So every symmetric function is in TC0. Okay. So every symmetric function can be computed by a threshold circuit, by a TC0 circuit, basically that is by threshold gates which have constant depth only. Okay. So the proof is actually not very difficult. It is just understanding how these functions behave. So given any function, okay, so given a symmetric function f, let us say, there exists a set S, okay, which has values b1 up to some bm, and these bi's are subset of the set from 0 to n. Okay, so let us say this is the, so do you use this, so is this representation used for the set from 1 to n or 0 to n? 1 to n, right? Okay, so then I will add 0 also. So I will add 0 to it. I need 0 to be here as well. Okay, so there exists an S, there exists a set B1 to Bm which is a subset of this, such that f of x1 to xn equal to 1 if and only if sigma xi, I going from 1 to n, belongs to S. Okay. So let us try to just understand this equivalence over here. So what is this saying? So think of S as the think of S as being the number of ones, okay, on which the function f evaluates to true, evaluates to 1. Okay. So f can actually evaluate to 1 on many inputs, right. Now on all, just look at all those inputs and divide them into sets, or divide or partition them into sets such that in each partition you have equal number of ones. Okay. So these are basically my B1 up to Bm. Okay. So maybe there is some input on which I have no ones at all. Okay. So that is basically the 0, and then I have some other input on which there are 2 ones, some other input on which there are 5 ones, and so on. But the point is that if I have one input which has 5 ones on which f evaluates to 1, then every input which has 5 1, f must evaluate to 1. That is by symmetric, because no matter how I permute those 5 ones, I must be getting the function must evaluate to 1. Similarly, if let us say f evaluates to 1 on again some other number of ones, it must evaluate to 1 no matter how you permute those quantities. Okay. So that is essentially what this is saying, that there exists a set this, and now what I am saying is that if I sum the number of ones that are there in my input, that must belong to this set. So there exists a set such that this is belonging to here. Okay. Is this clear? M is some number, M is an arbitrary number, it depends on the specific function. So M essentially means how many ones are there, or wait, look, let me, how do I phrase this? So M means that yeah, so how many ones are there on an input on which f evaluates to 1. For example, I will give you an example. For example, the parity function is actually a symmetric function, because no matter how you rearrange the inputs, it will always evaluate to true. Now for the parity function, what will your S be? Any guesses? What will S be? The set of odd numbers. Okay. So here the set S will be 1, 3, 5, 7. So up to so we have n, right. So let us say if n is odd, so it will be 1, 3, 5, 7 up to n. If n is even, it will be up to n minus 1, whatever. Okay. Exactly, that is what I said. The number of ones on which the function evaluates to a 1. Okay. That is the only thing that is necessary. Okay. So now how do I write this? So this I can write as, so this belongs to S. So now S can have any value between this. So this can be written as OR of let us say J belonging to S sigma xi equals bj. Okay. So it means that there is some not j in S, but j in or bj in S, let us say, whatever way you want to represent this, bj belonging to S such that this is equal to bj. And now this can be written as how can you write this as a threshold function? So I can write this as sigma xi So if my threshold function was greater than or equal to, right? So this is greater than or equal to Bj and sigma of minus xi is greater than or equal to minus Bj. I don't need a thing. This is not needed. Okay. So basically, I am not doing anything fancy over here. I am just saying that a quantity is equal to another quantity if it is less than or equal to and it is greater than or equal to that quantity. And greater than or equal to fine, I can represent it using a threshold gate, that is a definition of threshold. But for less than or equal to, I have just put negative. I am just switching the thing, I mean, to the other side. Okay, that's all. And this is basically, so what we have is a depth. So here I have a threshold, here I have one level, then I have an AND gate at the top, and then I have a OR gate. So it is a depth 3 threshold circuit, depth 3 TC0 circuit of whatever linear size. Okay. So as I said, immediately as a corollary, what we get is that parity is in TC0. Okay. So now let's come back to this relation over here. So for example, we have the parity function. We have showed that parity is in TC0. So the natural question is to ask, is it in AC0 as well? Okay. And that is another, I mean, there is a sequence of very famous results which prove that parity is actually not in AC0, and we will come back to those proofs in the second half of this course. Okay. And they are not just proofs which showed that parity is in is not in AC0, but they actually developed very nice techniques. Okay. So they actually developed very nice techniques to show that, which are useful for other results as well. Okay. So which are useful for proving lower bounds in for other functions as well. Okay. So this is kind of what we have. Okay. So any questions? This we know is a strict containment once we prove that parity is not in AC0. Okay. So far we still don't know, but once we prove that parity, so we have just proved that it is in TC0, and once we show that it is not in AC0, it will be a strict containment, but this we don't know. We don't know of any function which belongs here but does not belong here. We don't even know whether this is a strict containment. We don't know if there is a function in, for example, which is in NC1 but not in TC0. We don't know that.
So that TCI is
We are showing for 0. Yeah, so that's a good question, that does it generalize for any I? I am not very sure, but I think it should be true for any I, but I am not very sure. I cannot certainly say that yes, that is true for all I, but it is certainly true for 0. Okay. So one exercise, in fact, I mentioned this earlier for you to try out, is to show that iterated addition is in TC0 in fact. Okay. Yeah. So if you allow threshold gates, you can do it in constant depth. Okay. Okay, so moving on. Hmm?
Addition to be AC0.
How? Uh, I think it is in AC0 because so addition of two numbers, right? Yeah, because if you look at, yeah, exactly. If you look at that carry-Lucas adder, you can actually do it using with a bounded depth circuit which has unbounded fanning. Yeah, that carry-Lucas adder is actually a AC0 circuit. Yeah. Okay. So now we move to the next arithmetic operation, that is division. So division is actually a very interesting operation for many reasons. First reason is of course that division need not be precise. Okay, so we can have two numbers such that if I divide one number by the other number, it may not have a finite representation. But essentially what we are looking for over here is just precision up to some n digits. Okay, we are just looking at the quotient which has a precision up to some n digits. So the problem is we have input some x and y. Okay, assume they are some n bit numbers, and what we want to output is, let's say, the ceiling of this. Okay, just the quotient. I mean, you can actually, I mean, once you get this, you can actually show that you can also output the value of the, I mean, of the quotient up to some n terms as well. That is also possible, but whatever. Okay. And in actually what we will show is something a little different. So let me define another problem, reciprocal. So reciprocal is, we have input, let's say some number a, and what we want to output is one over. Okay, so we need some assumption over here. Okay, so this is let me just write this a little differently. So we'll assume that we have A such that A lies between half and it is less than 1 up to n digits of accuracy. Okay. So assume that A is a number between half and 1, and we are given A up to n digits of accuracy, and what we want to output is 1 over A up to the same accuracy. So what will be the value of 1 over A? Where will 1 over A lie? So note that 1 over A will be between 1 and 2. Right. So 1 over A is greater than 1 and it is less than or equal to 2. This is what we have, and this is what we want to output. And the reason why these two problems are somewhat equivalent is because computing x divided by y is the same as computing x into 1 by y, right? And x multiplied, and we know that multiplication is in, well, once we show this, we know that multiplication is in TC0. Okay, so basically these two problems are what are called TC0 equivalent. Okay, so given, let's say, this problem, I can reduce it to reciprocal by using a TC0 circuit. Yeah, so what is the significance? So actually we will need this in our calculation, but the point is that this is actually not a very big restriction. The reason I will tell you why. So, suppose you are given any number, okay. So, let us say that okay, let me write this properly. So, why we can assume without loss of generality that is between this. Okay. The reason is, suppose you are given any arbitrary a, suppose any arbitrary integer a. What you can do is you can keep dividing a by 2 until it falls below 1. Okay. So, essentially given a, there exists a number k greater than, or it can be 0 also, yeah, greater than or equal to 0, such that a is equal to two to the power k into some a prime, such that a prime has this property. Okay. And how large is k? So, k is as large as logarithmic in a. Okay. So, essentially by you can very easily create a log depth circuit which can do this for you. So, it will take any number and it will keep on dividing it by 2. So, it will find a number k such that dividing a by 2 to the power k will give you this required number, and then you do the entire process with a prime, and finally what we will do is we will just multiply it back with 2 to the power k and we will get the original reciprocal. Then you multiply it with something, you multiply it with, so you just, yeah, so if it is, let us say, less than enough, then you multiply it with 2 to get it between this, the same argument. Okay, so now that we have this assumption, let us try to see how we can do division. So, division is actually, there are many methods. So, in fact, even our next lecture will be focused on division, but what we will show today is one of the very basic methods, and this is based on the Newton-Raphson approximation of any function. Okay. So, consider the function f of x, which is equal to x minus 1 over a. Okay. So, essentially the roots of this function is basically the value of the reciprocal. So, for whatever value f of x is equal to 0, that is the reciprocal. So, essentially what I want to compute is the root of this function over here, right. Is this. Now, how do we compute the root of this? So, what we will do is we will solve this in a iterative fashion. Okay. So, first we will guess some value, we fix some arbitrary value as my root. Okay. So, we start with some x naught. Okay. So, we start with some x naught. Okay. Then, okay. So, we start with some x naught, okay, as the initial estimate, and as I said, use NewtonRaphson's method to get better approximations. Okay. So how do we do? So we all know this. So let's say we have some xi. So xi plus 1 will be equal to xi minus 1 second. Okay, fine. F of xi divided by f of x, f prime of xi. Okay, so this is how we get closer and closer approximations of the root. And now what is f prime of xi? So we know that f of xi is x minus a of I. So this is nothing but, if I look at the first derivative, it will be, yeah, this should be actually one over x minus. Okay, so we'll take fx to be this function, 1 over x minus a. Okay. Yeah. So then this will be xi plus f so fxi is nothing but 1 over x minus a. Now divided by the derivative of this is minus 1 over x square. So this becomes a plus, and I get x square over here. Okay. So this is equal to xi plus xi minus a xi square, which is equal to xi 2 minus a xi. Okay. So basically to compute xi plus 1, I need one multiplication over here, then one addition or subtraction, whatever you want to call it, and another multiplication. So basically two multiplications and one addition. Okay. So now the question is, how many times do I have to do this? So as I said, that I want to get the value of 1 over a up to the same level of accuracy. Okay, so I start with some initial estimate, and let's say I do this once, so I will get x1, x2 and so on. But how many times do I need to do this? How do I estimate the accuracy? So first of, okay, so let's say, so what is the initial value? So we start with x0 equal to 3 over 2. Okay, so if we start with x0 equal to 3 over 2, yeah. Now let's calculate the error term. Okay, so we will calculate the error term after each iteration. So what is the error term initially? So initially I will have epsilon 0, okay, which is equal to okay, 1 over a minus x0. So x0 I start with 3 by 2. Okay. So if x0 is 3 by 2, then 1 over a minus 3 by 2 is, so 1 over a I know is between. So error term means that at every step I calculate xi. How far is xi from 1 over a? What is the difference between 1 over a and xi? Okay. So that should converge, and that should converge quickly for us. So we have to show that in a small number of iterations I should get accuracy up to n bits. That is what. Okay. So okay, so let me just write this. So the error term, let's say after the ith step, it is ei is defined as 1 over a minus xi. This is the error term for us. So initially this is 1 over a minus x0. So 1 over a is between 1 and 2, and I take x0 to be 3 by 2, that is 1.5. So this is basically less than half for us, less than or equal to half. Now we will try to estimate what ei plus 1 is, or epsilon I plus 1 is, in terms of epsilon I. Okay. So what is epsilon I plus 1? So epsilon I plus 1 will be 1 over a minus xi plus 1. And what is xi plus 1? Xi plus 1 is in terms of xi, it is minus 2xi plus a xi square. And if you actually rearrange this, what you will get is a into 1 over a minus xi whole square, which is equal to a epsilon I whole square. Okay. So essentially, and what do we know about a? So we know that a is less than 1. So therefore this quantity is less than epsilon I. Okay. And not just, yeah, so and not just it is less than ei, essentially the error actually reduces by a factor of quadratic. Okay. So at each level the error kind of I mean the number of precision digits in 1 over a actually doubles. So after each iteration, the number of precision bits in x I because I have a quadratic factor over here.
So if there is a quadratic factor, then it's double. So if there is a cubic factor, triple.
If there is a cubic factor, then yes, it would triple, the number of bits will triple. Okay.
Then the growth of this accuracy is exponential.
Huh?
The accuracy is exponentially increased.
Exactly. So we only need log n many levels to get to a accuracy of n. Okay. That is exactly how it works. Therefore, in order log n iterations, we get n bits of accuracy, and that is what we want. So essentially, what is this thing now? So we do this in an iterative fashion. So at each level we are doing essentially multiplication and addition. Okay, so that is like so if you are looking at NC circuits, that is like log depth for us, and here we have another additional log depth. So therefore, division is in NC2. Okay. So this gives us an NC2 circuit for division. So now the question is, can we do better than NC2? Can we do it in, for example, in TC? Huh?
Log n times y is multiplied.
Where?
So why is it getting multiplied by log n?
Oh, because we have to do this multiplication. Na? So sorry, this one. So from xi to go to xi plus 1, we are doing multiplication and addition. We know that multiplication takes log n, and this we are doing log n time. So that's why we get log square. Yeah, so next we will see how we can improve upon this, how from NC2 we can actually come down to smaller depth circuits. Okay, so I'll stop here today.